Yeah, can anyone tell me what is the short channel and what is long channel you mean by? Anyone in the group? Small width of channel. Small width. What do you mean by small width? How you say this is the small width? How I should say that 22 nanometer is the small width? Why I can't say 1 micrometer or 10 micrometer is long width? On what basis I say? Less than length of the channel, less than length of the channel. Come on. Channel itself is the length, right? Yeah. Anyone else can respond to this question? What exactly I mean by or we mean by a short channel? So it goes something like this, okay? What exactly we mean by the short channel, okay? Suppose if I take uh, this is my n plus, okay, and this is again my n plus. Okay, so these are the two things that I have, and this is what exactly I mean by the channel. Okay, so this is the channel, irrespective of the short or the long transistor. This is what we mean by the channel. Okay, so channel length basically the space between the source and the drain we have. Okay, so this is what exactly is all about. Okay, so now when this channel length, okay, this is exactly the body we have. Okay, then without any biasing, okay, we can expect a depletion region. This is p type, this is n plus and this is n plus, right? So this is a pn junction formation, this is pn junction formation, and we all know that under unbiased condition, okay, so when the diode is not under any bias, okay, there will be a depletion region. Okay, so we can say that this is the depletion region that is existing between the p and n of this, and this is the depletion region that is existing between the p and n of this. Okay. And now this is where we try to define what exactly we mean by the short channel. Okay, so short channel is basically, okay, we try to define as equivalent to when the short channel, when the length, when the length of the channel is comparable with the summation of two widths of the depletion region. Okay, okay, so what I do here is go here. Okay, just continue here. Comparable with the summation of two width of the depletion region. Okay, so this is what I mean by when the length of this channel, okay, this is what, okay, so when this channel length, what I am defining now, okay, when this length is comparable with the summation of two width of the depletion region. This is one width I can say, okay, this is another width. Okay, if I say that this is somewhere around 0.2 micrometer, okay, and this is again 0.2 micrometer, okay, and it is somewhere around 0.5 micrometer. If I just assume the length of the channel is something like 0.5 micrometer, whereas the depletion width, one at the source region and the another at the drain region, they are 0.2 micrometer each. What is the summation of these two widths? It is 0.4. Okay, so summation of two widths is 0.4 micrometer. Okay, whereas the length of the channel is 0.5 micrometer. This is one. Suppose if I have another channel, okay, which I call it as something like the length is more compared to this now. Okay, again this is the width with respect to the source, and this is the width with respect to the drain. and this is what my channel length is all about now. And I assume that this is somewhere around 10 micrometer. Okay, and the width is remaining the same. Okay, the PN, this is again 0.2. Okay, whatever the width I'm saying here is again the 0.2 micrometer. It is 0.2 micrometer, and here also it is 0.2. Okay, again if I summation add both the width of this depletion region, it again comes to 0.4 micrometer. Okay, this is again comes to 0.4 micrometer, whereas the length of this channel here is 10 micrometer. So there are two examples. One where the channel length is 0.5 micrometer and the sum of the width of the depletion region are at junction at one at source and another at depletion is 0.4. And the second case I have where the channel length is 10 micrometer and the sum of the depletion width of these two are 0.4 micrometer. So according to this, so in these two cases, in which case I can say that length is comparable with the summation of the width of the two depletion region. Is it the first case or the second case? I don't know message. You can unmute and tell me fast. Yeah. So in which case one or case two, we can say that the channel length is comparable with the sum of the width of the depletion region. Case one or two?
Sir, first case, sir.
First case.
First case.
Yeah, case one. So that's what. So if someone asks you what exactly you mean by short channel, or when you say that transistor has a short channel, if someone asks you, you should be in a position to tell that whenever the length of the channel, okay, is comparable with the summation of the two width of the depletion region. When this L is comparable with these two widths, addition of these two widths, then I can say it is a short channel. Whereas in the second case, 10 micrometer and 0.5 micrometer, this cannot be compared. Okay, so it is more than 9.6 micrometer difference. Okay, so this is what when the channel length is not comparable with the sum of the width of the depletion regions, then it is called a long channel. And when the length of the channel is comparable with the summation of width of the depletion region, we call it as a short channel. This is what the definition of a short channel is all about. Hope it's clear. Fast. Response. Okay, so this is what we have, and then as sessions, there are, even though there are a lot of advantages with respect to the short channel, but there are some non-ideal characteristics or the secondary effects, what we call, especially in the short channel. Okay? So one of the non-ideal IV characteristics or the secondary effect is the subthreshold conduction. We'll see what exactly the subthreshold conduction is all about. The second is the body effect we have seen, but anyhow we'll try to see what is the other impact of this body effect. And the third is channel length modulation. This is also we have discussed, a brief information we can give. Then the velocity saturation and mobility degradation. We already seen the velocity saturation, meaning when the VDS increases, okay, beyond VGS minus VT, okay, then we can say that the current saturates, and this current saturation is typically with respect to the gate losing the control on this, okay? And we'll see what exactly this mobility degradation is. Then tunneling, this also we have discussed. This is basically when the oxide thickness keeps on decreasing, okay? Then we have junction leakage, already discussed, but we'll have a quick revamp of this. And then the temperature dependency of temperature dependent of the transistor. Okay, so this is what we have. And starting with, we'll first take one of the non-ideal IV characteristics, that is the subthreshold conduction. Okay, so this is the first one that we'll try to see now. Okay. Now, when I say subthreshold conduction means, in order for transistor to on, for example, if it is an NMOS, okay. So for an NMOS, basically we say that in order to on the transistor, okay, so we want the VGS. So typically we want VGS should be greater than VTH or VTN, for that is the case. Okay, this is what. So in order for the NMOS to be on, okay, so we have to provide the gate voltage minimum or greater than. Okay, so either minimum, that is equal to VTN, or greater than, in order to switch on. Okay, but this is what. So this only when I can say that the current may be existing, okay, when I have the drain to source potential application. Okay, so this is what. So when VGS is greater than VTN, ID exists, okay, provided there is a drain to source voltage that is appearing. Okay, the moment my VGS is less than VTN, can anyone tell me what will be or what should be my ID? Fast. The moment VGS is less than VTN, what should be my drain current or drain to source current? Yes? Fast. Yeah, the moment VGS is less than VTN, what should be my drain to source current? Please don't message, respond using mic. What should be my ID? Fast.
Sir, it will be 0, sir.
It will be 0. See, if you people doesn't respond immediately, I will call by name and you should answer me. Is that clear? Yes? Okay, so we ensure or we know that the moment VGS is less than VTN, I want ID to be 0. But because of the non-ideal, or because of the secondary effect, or because of the short channel, even though when VGS is less than VTN, okay, when VGS is less than VTN in short channel, okay, in short channel, ID no more remains 0. It is not a 0, it is a non-zero value. Okay, and that is what ID is not 0 means what? There is some current flowing. Okay, so this is what, when even though when the gate to source voltage is less than the threshold voltage, there is a conduction happening, and this current is nothing but what? The sub-threshold conduction. This is what I mean by, or we mean by, sub-threshold conduction. And why this happens? And we know that until we provide VGS equals VTN, there won't be a channel created. And now we are saying that even though VGS less than VTN, that means without formation of the channel, there will be still the drain current. What does this mean, right? Okay, this is what exactly we try to see in the next subsequent slides. Okay, what we mean by subthreshold we just now saw. Okay, but now the next thing is what exactly or how exactly this current exists or the transistor starts conducting before the VGS is less than VTN and all. Okay, so this is what we have. So now, as we were saying, okay, so we will take up a simple NMOS transistor. This is an NMOS transistor for me. Okay, so this is basically an NMOS transistor. Okay, with the substrate P, this is N plus and this is another N plus. Okay, so we have a gate here. Okay, right now I'm not interested in the gate, source and drain, but still we can still consider what exactly these three are all about. Okay, so P, N plus, this is the gate, source and the drain now. Okay, so if you remember, we had one session on the energy band diagram. So now what we'll try to do is we'll try to analyze this NMOS transistor, okay, to ensure what exactly the subthreshold conduction is all about. Okay, this is N, this is P. One PN junction or P-type N-type material, and here also I have one P-type N-type, or in other words I have N-type, P-type and N-type. And in N-type we know that the Fermi level will be near the conduction band, and in p-type, the Fermi level will be near the valence band. Okay, and now if there are three different independent components, the Fermi level along with the conduction and the valence band are okay. But now when they come in contact, N, P, and N come in contact, we have something less. So this is the energy diagram. Okay, so this is typically energy diagram. Okay. Energy band diagram for this particular case. This is okay. So this is an NPN. This is what I mean by N. Okay, and you can see that formula is EC, and this is my B. And you can see that foam level is away from EC, but it is near the EC. So this is the V of P-type, this is the EC of P-type. And again, when I come towards another N region here, you can see that the Fermi level is near the EC. So this is N, P, N, and when exactly the Fermi level will be aligned? Can anyone tell me when the Fermi level of N, P, and N will be aligned? Under what condition the Fermi level are aligned or have the same Fermi level? Yes? Yes, Monica? Monica? Yes, Bhumika Rani? If you don't respond, I immediately mark you people as absent. Okay, so that's what I'm doing now. Okay. Okay, Anubhav?
Yes, sir.
Yeah. So I don't know why you didn't respond at that time. So my question is simple. Okay. So I have a three material N, P, and N, and I know that in the N type material, my Fermi level is near the EC, and in my P type, the Fermi level is near EV. Okay. And now, in this particular energy band diagram that we have, I'm showing here. Okay. Here, the Fermi level is aligned with all the three. Okay, so under what condition this Fermi level will be aligned and it is straight? Yes? Yes, Anusha? Yeah, Bhumika and Monica are already absent. I don't know how many else will be absent today.
Yes, sir.
Yes, Anusha, you got message now?
Yes, sir. Your voice was breaking, sir.
Oh, okay, okay. So till this point you didn't add voice break, but the moment I asked question, you have a voice break. Amazing. And you didn't tell also. You didn't tell also that my voice is breaking. Amazing.
When you were explaining,
When I was explaining, it was breaking.
yes, sir.
Okay. You want me to repeat the question again?
Yes, sir.
Okay, good. So my simple question was, if this is my NMOS cross-sectional view, I have an N-type material, P-type, and N-type, and the corresponding energy band diagram I have written here. Okay, this being the one N, which is the source. This is the P, which is this channel kind of thing, and this is another N, which is nothing but what the drain. Okay, so and you know that the Fermi level of N type is near my EC, and the Fermi level of P type is near my EV. That is all the fundamental thing. Next, the second thing I asked is that my question is simple. In what condition the Fermi level of all these three materials is aligned?
So when P and N are together, like when the junction is formed, the
They
Fermi
have already
level-
formed the junction. They have already formed the junction. My question is simple. Under what condition there is a alignment in the Fermi level? Mahendra?
Yes, sir.
Yes, sir. Please, sir.
That's what when we bring them in contact, sir.
I know that I bring them in contact. When I bring them in contact, need not that the alignment of the Fermi level should happen. It can be different also. The Fermi level of P type may be different from the Fermi level of N type,
Yes,
or
sir.
the Fermi level of two N types may be different when I bring them in contact. Under what condition is the Fermi level will be aligned and the same? No doubt it is when I bring them in contact. Yes, Geeta Patil? Geeta Patil. Yes, Sumant? Sumant? Yeah, Sumant is absent. Geeta is Patil is absent. Monisha left. Someone else left. Okay. Jagdish?
Yes, sir.
Yes, sir. Hope you have listened to my question, right?
Yes, sir.
Yeah, tell me, sir. Under what condition, when I bring two or three different materials, will be aligned? Anyone can help your friends? Yes, Sushank. Yes.
Hello, sir.
Yes, sir. Tell me, sir. When I get or when the Fermi level will be aligned when I bring two or more three different materials together. Under what condition? When electrons and holes travels in the same concentration. Under no bias condition. Akhil, under no bias condition. Okay. So exactly under the unbiased condition. Okay. So under unbiased condition, you can just see now I have not applied any biasing either to the source, the gate, or the drain. And the moment I bring all three together in contact, my Fermi level will be leveled. Okay, and this is what I mean by the barrier right now. Okay, that means electrons which are here, okay, and the electrons which are in this side, okay, they don't have that much of energy or the potential to cross this barrier and come towards this region. Okay, then this is exactly what the barrier it is all about. Is this clear? Okay, so when I bring two or three materials in contact to each other, okay, under unbiased condition or no bias condition according to the Akhil, we say that the Fermi level are aligned and straight. Okay, this is one thing. Now, what exactly I try to do is I start applying my drain to source of voltage. Okay, so that is what I'll try to do. I'll try to apply now the potential between the source and drain now. So the drain is at positive potential, and this is obvious. We have seen during the NMOS working. Okay, so my drain is at positive potential of the battery and my source is at negative potential of my battery. Okay, under this what really happens now? Okay, so this is an N type is given to positive potential of the battery, and this finally referred with respect to the ground, and we are seeing that the body or the substrate is connected to ground. In other words, I can say that my source and my body are of the same potential. So okay, this is what really happening now, and this N type is at what potential? It is that positive potential. Okay, so what really happens to this PN junction diode now? what really happens to this PN junction diode when this N plus is connected to positive and this P is grounded now? What really happening to the PN kind of diode near the drain? Is it forward bias or reverse bias? Fast. Is it forward bias? It's a reverse bias, right? When I say reverse bias means what really happens now? Will there be current flowing? What happens to the barrier height near the drain now? What happens to the barrier height near the drain here? Fast.
Increases.
It increases, the barrier height increases. In other words, I say that this is what really happens now. The moment I start increasing my VDS, okay, now I'm applying the biasing. The first one was unbiased. This was unbiased condition, okay, wherein you can see the Fermi level, that is EF, is aligned with all the three materials type thing. Okay, this is my Fermi level, energy level of Fermi. Okay, this is EF. And now this, the second figure, what you're saying, this is under the bias condition, and VDS, drain to source, I'm increasing. In other words, N is connected to positive. That means N is becoming more positive with respect to my P type. This is reverse bias. I can see that this barrier is getting wider and wider now. Okay. Initially, this was the barrier now. Is that clear? This is increasing. But now you can see that this barrier increasing means this entire thing. Okay, so what really I'm saying is this entire thing, okay, is going down now. And that is what you can see, that's the significance of this. So this EC is moving down compared to this EC. Similarly, this EV is moving down with respect to this EV. It is coming down. Okay. So barrier near the drain is increasing, but what is happening to the barrier near the source now? Because of this decrease in this or increase in the barrier near, or the energy band is going a little bit down over here. What is happening to the barrier right near the source now? This is the barrier right near the source before the biasing. After biasing, the barrier right near the drain is increasing. But what is happening to the barrier right near the source now? Is it remaining the same, or is it getting reduced because the right portion is pushed down? Fast, anyone can respond. Fast. What is
Reduce.
Reduction.
Yeah, it is reducing, right? Suppose if I keep increasing my VDS again, I keep increasing my VDS again, you can see that the barrier height here, it is going down and down and down. But what is happening to the barrier near my source? Is it still decreasing now? Yes or no?
Yes, sir.
Yes. Now I can ensure the electrons which are near the drain, they can't climb up this hill because of higher the barrier potential. But the electrons near the source, the barrier is getting reduced, means one or the very few electrons which are near here, can they now just jump and come towards my drain region? Yes or no?
Yes, sir.
Yes, this is what really happening. So the moment I start increasing or applying the VDS and increasing from 0 to maximum or towards my positive value, I can see that the barrier near the source is getting reduced and the barrier near the drain is getting increased. Hence, the electrons in the N type, that to the source, okay, now the barrier is getting reduced, means I can say that few numbers of electrons now are sufficient energy to cross this barrier and come towards this. What I mean by electrons from source reaching the drain, what is exactly happening now? Fast. What we mean by the carriers flowing from source to drain, what is the final thing now?
Channel current.
It is
Channel
basically
current.
a current is established, yes or no? Current is established or not now? Carriers are moving from source to drain with respect to VDS. Is there current or not? First.
Yes, sir.
Yes, there is now current. Okay. So now I can say that, okay, the current starts, or the conduction starts, I can say. The conduction starts as we increase VDS, okay, from 0 towards positive, okay, towards positive thing something. Okay, so this is what really happening now. So as I keep on increasing my VDS, again here you can see that VDS is increased still more. That is what I mean by the double arrow here. Okay, the VDS is increased still more. The barrier is getting lower near the source, and this helps the electrons, few electrons in the source, to cross this barrier because the height is less now, jump and come here, and that constitutes what I mean by current. And now assume that my VGS is less than VTN. Okay, for example, if my VTN is somewhere around 0.4 volts, okay, VTN is 0.4 volts, but now my VGS is equal to 0.3 volts. Okay, this is what the condition I'm taking. Okay, so VTN is 0.4, I'm assuming. Okay, this is VTN is 0.4, I'm assuming. But now the actual VGS value is 0.3, which is less than 0.4. Okay, even though VGS is less than 0.4, okay, there is no channel, but there is current that is flowing between source and drain. Am I right? Am I right here?
Yes, sir.
Yes. So what exactly this means now? What exactly this means? That means the gate to source voltage doesn't have control on the channel now. It is the VDS that is having a control on the channel. In other words, when VGS or when VT, as my VT is getting reduced, is VTN is getting reduced? As I am increasing my VDS, okay, even though VGS is less than VTN, I have the current over here. Yes or no?
Yes, sir.
Yes. In other words, can I say that the current exists even though my VGS is less than VTN? Yes or no?
Yes.
Yes, sir.
That means no more current will be zero when VGS is less than VTN. Okay, it will be a non-zero component. Why this is non-zero component means as we keep on increasing my VDS, okay, in towards the positive value, okay, and in the short channel transistor, we can ensure that the barrier near the source is getting lowered, because of which my electrons starts reaching towards the drain, constituting the current. And this current is what we know as subthreshold current. What is this? We call this as subthreshold current, or we call it as something like a subthreshold conduction. The other significance or other takeaway point over here is, now when I say this is still an enhancement, this is still an enhancement mode transistor now. This is still enhancement type now. Enhancement type NMOS now. Still it is enhancement type. Means what? There should be channel now existing. But now what it is happening now? before channel I am seeing the current to be there. In other words, I can say that the VT is reducing, yes or no? Fast. Until now, we were under conclusion that, or we were under the meaning that I want minimum, okay? I want minimum VGS to be VTN, okay? For current ID to be non-zero value, okay? So for ID to be a non-zero value, okay? But now, because of this short channel, we are seeing that even though VGS is less than VTN, okay, VGS is less than VTN, okay, ID is still non-zero. What the meaning of this is? What is the meaning of this? What is really happening to my threshold voltage here? Is it increasing or is it decreasing now? Fast. What is happening to the threshold voltage now?
Kind of decreasing, sir.
It is a kind of decreasing now. It is a kind of decreasing, meaning I want VTN to be 0.4 and VGS to be 0.4 in order for current to be there. But now, even when VGS is less than 0.4, that is 0.3, there is a current means what? My VT is reducing, and this is what is really happening now. Okay, so what really happening is now, if I just plot the graph VT versus the channel length now, L, this is my x-axis is with respect to the length, and y-axis is with respect to VT. And if the channel length is long, or when I say a length of the channel is long, or the long channel, my VT remains constant. Okay, there is no change happening now. But the moment when the channel length starts decreasing, okay, what really happens to my VT? Fast. What happens to my VT? The moment the channel length, the moment channel length decreases, my VT starts decreasing. VT starts decreasing in terms of this. Is that clear? And this, I can say that the decrease in VT is possible only in short channel transistor. This is what really happening. Whereas for a long channel, all this, whatever you are seeing, this constant VT no more decreases with respect to the VDS. This is all with respect to the VT is getting reduced in a short channel transistor because of what? Because of VDS. This should be there in your mind now. As I keep increasing my drain to source voltage in short channel transistor, my VT starts decreasing. Okay. This is one case. And other thing that we saw is, no doubt the VT is decreasing, but the barrier near my source is getting reduced. So that's why this particular concept where the source barrier is getting reduced is called as DIBL. DIBL. What I mean by is drain induced barrier lowering. What I mean by drain induced barrier. It is the drain, okay? This is the drain voltage, okay? That is VD with respect to the source. This is the voltage. The moment I start increasing towards positive, 0 to positive, towards positive, okay? This reduces the barrier near the source, not near the drain, okay? So that's why it is called drain induced barrier lowering, and barrier lowering is happening at the EC. Because of the barrier lowering near the EC, there is a movement of electrons, or the electrons from N type, that is source, will go towards my drain region. That's constituting the current, even though VGS is less than VTH. Or in other words, I say that as my length decreases, my VT also decreases. Okay, this is one significant thing that we want, okay, in order to see what really happens with respect to the current when VT decreases. Okay, so we have this expression of current, that is IDS, which is given by, and you know that IDS is basically ID versus VG is an exponential, right? And that is what this exponential is all about. IDS is equal to ID naught. This is the saturation current into e to the power of VGS minus VT divided by neta VT. This is non-ideal factor. For an MOS transistor, this non-ideal factor may be neta may be 1.4 to 1.8. This is temperature equivalent to voltage. This is basically capital V, capital T is with respect to voltage equivalent temperature. At room temperature, what is the voltage? This is basically 26 millivolt that you have already studied in your PN junction diode. This is the threshold voltage. This is gate to source voltage. This is drain to source voltage, and this is again the temperature equivalent voltage. Okay. So now here, when VDS is 0, okay, that means when this becomes 0, okay, e to the power of minus 0, it is nothing but what? 1. Okay, this entire thing becomes 1 when VDS is 0. 1 minus 1, my IDS is 0. The moment I am up, the moment I don't apply my VDS, that is the drain to source voltage, my IDS is 0. That is what this particular equation says. Okay, this is 1. Next, if this is not 0, if VDS is not 0, this VDS is some positive potential. Okay, it is some positive voltage. Okay, and we know that as my VDS increases, what happens to my VT? So as my VDS increases in the short channel transistor only, we saw the threshold voltage decrease. That means when the moment this increases, we saw this getting decreased. And when this VT gets decreased, what will happen to my IDS? Fast. What will happen to my IDS? Fast. Anyone can respond. What will happen to the current? Whether it will increase or decrease in terms of exponential?
Increase.
It will increase, right? Exponentially it increases. This increases now. And that's what we saw now. When VT is less than something, there is some current. Okay, so there will be current now. So now what we'll try to do is we'll try to plot the current versus the threshold voltage. Okay. In the previous graph, we saw how the threshold voltage, what is the effect of threshold voltage with respect to the length. Okay, if the channel length is long, VT doesn't decrease. If we increase in VDS, the moment the channel is short, or in a short channel transistor, the moment VDS increases, the VT decreases. Okay, and now what we are saying is, now we'll try to plot the current in terms of log. Okay, take the current in terms of logarithmic, easy for us to draw. Log ID versus VT. Okay, so sorry, with respect to the VGS I am going with, I just okay. This is my voltage and this is my ID. IDS all are one and the same for me. Okay, so assuming that this is my actual VT. Okay, this is my VT. Okay, VGS greater than VT. Okay, anything above VT, log ID, so it is constant. Okay, with respect to VGS, the moment VT is reducing, the moment VGS is less than VT, we want something like this, right? This is what we want. Sorry, we want something like this. The current should immediately become 0. Yes or no? Fast.
Yes, sir.
Yes, but actually what really happening now? Actually it is not becoming immediately 0. There will be some current. Okay, so this is what we mean by sub-threshold current. This is what the current. So this is what we mean by what we discussed just now is the sub-threshold current or sub-threshold conduction. Okay, that means you can see that even though VGS is less than VT, there is a current that is there. But actually, ideally, we wanted the current to be zero the moment the gate to source voltage is less than VT. Okay, and after this, what I mean by constant? Because the current depends upon the VDS now. Is that clear? So the current increase or decrease, the moment VGS is equal to VT, it depends upon the VDS. Okay, and this is what is exactly now. So as my VT decreases, okay, there is a current that is flowing, and in terms of log, I am showing this. Okay, so this is what we mean by the sub-threshold current. Hope this sub-threshold current or sub-threshold conduction is understood fast. Shall we move on to the next concept? Yeah. Yeah.
In the end, that last graph you drew, no, sir.
Yeah.
Where VT was, how did the current decrease there, sir? Like ID is goes on decreasing when VT 0 to VT.
0 to
VT
no.
ID was
What do you mean by log ID? What exactly we use the log ID?
it's
Why have
logarithm
take?
IDS.
Yeah. What is the difference between an ID and the log ID?
I don't know, sir.
Yeah. Can anyone tell me why I have plotted ID log with respect to that? Yes. Yeah. Why did I drew something like this now? This is my VT. Okay. Anything VGS greater than this, this is constant. Anyone tell me why I drew this in terms of logarithmic?
So the equation is in terms of exponential.
Equation is in terms of exponential. Okay, good. What is the impact of that on this?
We remove exponential, sir, by applying law.
Okay. Okay, so that's one thing. And now that means it is not that when VT decreases, current is increasing. In other words, what I mean by is, if VT is 0.4 volts, assuming that this is the threshold voltage of MOS transistor, okay, NMOS transistor. Okay. Now we understood that if VT is 0.3 volts, if VT is 0.3 volts, VT is 0.3 volts here. Ideal case, what should be my current?
0.
0, right? My current should be somewhere over here, 0. Still, if my VT is 0.2 volts, suppose if VT is 0.2 volts, again ideal case, again the current to be 0, right? Yes?
Yes, sir.
At VT, I say it is on. That means there might be current because of the VDS. So that's why I'm just drawn here, okay, in terms of normalized kind of thing. Okay. So after this, there will be a current, that's what I'm saying, and that current increase or decrease. See, there are two aspects now. ID versus VDS. Okay, now can anyone tell me what is the relation between ID and VDS? As VDS increases from 0 to something, what happens to my ID? Will it increase? Provided my VGS is equal to VT. Yeah, what is the relation of ID versus VDS? Provided VGS is equal to VTN now. Come on. Fast. What happens to, so I assume It increases. Initially, it increases linearly. Then what happens? At pinch off, it saturates and becomes almost constant. Or because of the channel length modulation, it won't be a constant. It will be increasing in this manner. Okay, this is with respect with channel length modulation, with this channel without channel length. Okay, and the moment I say the transistor is on, okay, this is with respect to VGS, right? If my VGS is equal or greater than, I say transistor is on, there will be a current depending upon VDS, that's why it is constant. But as we saw in this drain induced barrier lowering, as VT is less than 0.4 or when VT decreases, still there is current, right? Yes or no?
Yes, sir.
Yes, and that current will be what? Will it be more than what actual, or it will be below, or that current may be less? It will be sub-threshold. It will be minimum current, because I'm not saying that all the electrons in N type, that is the source, will reach here. No, only few electrons which are here, they might reach here. That constituting some current, and that is what we mean by the sub-threshold current. And that current may be somewhere over here if VT is 0.3. Is that okay?
Okay, sir.
If VT is 0.2, what really? Will the current will be higher or lower here?
Lesser.
Lesser. Okay. If I try to plot now, it goes something like this. Is that clear now?
Yes, sir.
Yeah, this is what is really the log ID versus the VGS graph. The moment VT is, see here we are just showing that the moment VGS is less than VT, I want the current to be immediately zero. I want the sharp slope over there, but I am getting what? A slope now, okay, which is not sharp, which is taking its own time. And this is nothing but what the current that is there, some current that it will be flowing, and that current we call it as a subthreshold current. Why it is subthreshold? Before or when VGS is less than VTN, okay, ideally ID should be zero, but in this case it is not zero, it is non-zero component. Oh, this is fine. Is this explained correct? Okay, yeah. So now, yeah. After this, now we'll go to what is called as a body effect. Okay, and again, when I say a body effect, again I'll just take a n plus. This is body. This is my p type. This is a typical NMOS transistor cross-sectional view. Okay, this is what we usually for an NMOS body we connect to what? First, NMOS body or the fourth terminal or the substrate we connect to what? Is it plus PD, a lower potential, that is ground we say. And this also the source of this is connected to, the source is connected to the ground. Yes, that is what, or the VSS. Okay, that means the source as well as the body are at the same potential. This is my drain and this is my gate. Okay, this is what. And this ensures that both the PN type near in the source region and drain region, they are the reverse bias, there won't be any leakage current. Okay. Now the other things happens. What is that is, suppose instead of I connect this body to some ground potential, suppose if I connect to some positive potential. Tell me what really happens now. Body is at positive potential. No doubt this is forward bias. This is also kind of forward bias. And in order for channel to establish, what should be my gate voltage? Whether it should be positive or negative for an NMOS?
Positive.
It should positive, right? Now you see interesting thing happening now. This gate is connected to positive and this body is also connected to positive. Now tell me whether the gate potential I should increase in order to enhance the channel here, right? What really happens to my gate voltage here, or the threshold voltage, minimum threshold voltage with respect to which I create a channel there? What really happens to my threshold voltage there?
Increases, sir.
Increases, meaning this is also positive. This is also positive, means the minority carrier, which are electrons in this particular p type, some electrons will be moved here and some electrons will be pulled down. Yes or no? Yes or no?
Yes, sir.
Yes.
Yes, sir.
In order to have an inversion means wherein the channel is completely formed. Okay. That means the gate voltage now exceeds beyond VT. Okay. Assume that if I had biased this body to the ground, VGS was taking minimum of 0.4 volts to get this channel to be formed, right? Now, since I'm connecting this body to positive voltage, will the same 0.4 is enough for the gate to create or establish a channel, or it requires more now? Fast.
Sir, more.
It requires more voltage, maybe more than the VGS should be greater than 0.4 now. It cannot be equal to 0.4, maybe 0.6 volts, maybe 0.7 volts. Okay, meaning the moment the body is not connected to the source potential or the ground, if I give some positive potential, the VTN starts increasing. The threshold start increasing. That means what is it advantageous or less? In order to switch on the transistor, there should be some minimum voltage applied, right? Yes or no? Yes, no?
Yes, sir.
Yes. But now what is happening now? VTH increasing means what? I have to apply more gate voltage in order to switch on. That means the device is getting more resisted with respect to this. Okay. So that is the body effect. Okay. There are two things. One is there is a current that is can establish between this PN and this PN, and that is what we mean by the junction leakage. Okay. And the other one is the body effect. What is the body effect? Because of the fourth terminal of an NMOS, if it is not connected to ground, if it is connected to positive, my VTH starts increasing, and this is not advisable. Okay, there should be minimum voltage in order to turn on, not the maximum voltage to turn on. Is it okay? Is this clear?
Yes, sir.
Yeah. Any questions? Any clarifications? Yeah. If no, then we'll move on to what is called this channel length modulation. Already we discussed. It is a simple thing that again I'll go through, wherein we'll try to cover this also. So we have covered the subthreshold. We have done this with respect to body effect. We have done with respect to the junction leakage. So now we are with this channel length modulation. This is N plus. This is N plus. Okay. This is what we mean by the channel. This is L, actual channel length. Okay. Now, if I keep increasing my drain to source voltage, okay, greater than 0, okay, and if the VDS equals the gate to source minus the threshold, okay, we say that the channel gets ceased. Okay, that means near this drain the channel ceases. That means it becomes almost 0. If I still increase my VDS greater than VGS minus VT, the channel, okay, length decreases. That means the ceasing of this channel moves towards my source. Okay, this is what really happens. Okay, as I keep on increasing my VDS, if it is equal to VGS minus VTN, the channel ceases exactly at the drain potential where the junction is. The moment if I keep increasing beyond VGS minus VTN, this is what happens now. Okay, this is my L, and because of the application of the VDS, this is my effective length now. This is my effective length. This is my effective length, and this is the difference of length that I'm finding it. Okay, this is, I can call it as delta L. Okay, so now for a short channel effect, when I apply the VDS and when the VDS is beyond VGS minus VTH, I can say that L effective equals actual length L minus delta L. Can anyone tell me the channel is getting reduced? Okay, what is the implication on the drain to source current or the drain current? What really happens now? Fast. What really happens? Yes, what really happens?
Sir, constant saturation.
Constant saturation, constant saturation, the moment I have this condition. Okay, you can see that at this point the current, but the channel is getting reduced. That means now what really happens now with respect to the IDS now? IDS versus VDS for the given value of VGS. This is IDS. Yeah, can anyone? Okay, for given value of VGS. So VGS, I say that greater than VTN. 0.5, 0.6, whatever. Now, as I keep increasing my VDS from 0 till VGS minus VTN, it is a linear. Everyone agree this is a linear? Yes or no?
Yes, sir.
Yes, almost kind of linear.
Yes, sir.
Then after the moment the VDS, it's VGS minus VTN, okay, the channel is ceased. That means no more carriers can generate, but the potential of VDS is such that the current still exists, and that is the carriers move at fast, so it becomes saturated. Okay, and it was supposed to be, it is constant at this point. Okay, and ideally we say that it will be constant elsewhere also beyond VGS minus VTH. But because of this effective channel length decrease, tell me now what really happens? Will it remain constant? Will it decrease or will it increase now? VDS is increasing. The potential with respect to which the electrons are pulled is increasing. Channel is getting reduced. What is the meaning of that? Channel is reduced means what? The distance between the source and drain is effectively reduced or not? Fast. Fast.
Yes, sir. It's reduced.
Yes. Yeah, it getting reduced means what? Now the electrons which are there in the source are reaching the drain at a faster rate? Yes, no. Yes, no. Fast.
Yes, sir.
Yes, sir.
Yes. Now the distance between source and drain effectively is reduced. The potential with which the VDS is attracting these electrons is more, means instead of being constant, there is an increase, slight increase in this current now. Is it clear what I'm saying?
Yes, sir.
Yes, sir. Yeah. So that's why you can see that when there is, this is what the channel length, this is channel length modulation happening. Because of the channel length modulation, I can see that the current beyond VGS minus VTN is not constant. It is increasing. Not significantly, but somewhat. Okay, compared to this is linear. I can say this is linear increase, whereas here it is not linear. It is kind of like exponential kind of thing. Is that clear? And this is what with channel length modulation, the current with channel length modulation, non-ideal case. This is without channel length modulation. Is that clear? This is what I mean by the channel length modulation, and what really happens with respect to your IDS when VDS is greater than VGS minus VT. Any questions? Any question? And this particular increase, it is not much increase, it is little increase. Okay, it is not much of increase. Almost the difference between these two will be in terms of some fraction of micrometer current difference. Okay, so it's not huge. Okay, this is what really about the channel length modulation. Then coming to the velocity saturation, simple. Velocity saturation means as VDS equals VGS minus VTN or greater than this, there are no new carriers that are there in the channel. Okay, so that means whatever the existing carriers are there, that have to maintain the velocity, and that is where it is getting saturated. Okay, that's what we mean by saturation, and that's what we can see that velocity is getting saturated, or the velocity gets saturated means what? The current also saturated. That's one thing. And there is one more concept called the mobility degradation. And you can see that mobility degradation, there are two aspects. One, this is the drift current that is flowing, drifting of electrons from source to drain. This is with respect to the lateral voltage, V lateral we say. Because of V lateral, that is VDS, we say there is a field existing because of lateral VDS, and there is one more field because of the vertical V vertical, and that field we say with respect to the gate to source. Okay, vertical. This is what we mean by the field with respect to vertical, and this is what we mean by the field with respect to the lateral. Okay, I'll take a few more minutes and we'll complete this aspect. Okay, so that's why I'm just continuing with this session. Okay, so because of this lateral field, okay, there is some mobility degradation happening with respect to the carriers. No doubt the carriers are moving in this direction. No doubt carriers are moving from left to right, from source to drain. But because of the vertical field, okay, the movement or the mobility of the electrons is affected. Okay, and that is what we mean by the degradation in the mobility. That means the mobility gets reduced. Okay, because of this vertical field. One thing. Okay, so the mobility degradation because of the vertical field, and also when the carriers are moving from source to drain, some of the carriers, the electrons, might hit the other electrons while they are traveling from source to drain. Meaning, if I have, this is my channel, okay, this is my source and this is my drain. When the moment the electron is moving inside this channel, it may hit one of the electron here and it may deviate from here, right? And it may hit one more and it may deviate here, and it may hit one more carrier and it may deviate. So something like this, okay, you can see that movement of electrons will not be in a straight path. It will be something like a zigzag kind of thing, or in all other direction. Okay, it may move inside, move up, down, or keep moving, and something like that. You can see that the path the electrons will take to reach from source to drain is not a straight, it goes something like this. So this is what we mean by the scattering of electrons inside the channel. And because of this scattering, there is a degradation of mobility. Okay, two things for degrading of the mobility or the movement of the electrons. One is with respect to the vertical field because of the gate to source voltage, and another is the scattering that happens when there is a collision of the carriers within the channel. So that's about your velocity saturation, the mobility degradation, the channel length modulation, the body effect, the subthreshold conduction. And coming to the tunneling, we have already seen the tunneling is because of the gate oxide reduction. Okay, so this is gate oxide. Okay, so this is gate oxide. Oxide obviously gives or resists the flow of current, right? Basically, it is all about the electrons and the holes. Okay, it resists. So that's why we say Ig, the gate current, is 0 in any MOSFET or FETs for that matter. Okay, because of. But now, as we keep on decreasing this oxide thickness, okay, Tox, if I keep on decreasing this, there might be chance that assuming that this is my oxide thickness, just very, if this is something like a 200 nanometer, this may be 10 nanometer. Okay, this is my oxide, this is my SiO2. You can see that now this was offering maximum resistance to the flow of carrier, but now what is happening now? This is not offering maximum resistance, it is offering minimum resistance. Minimum resistance means very few carriers may tunnel to this channel. This is what we mean by that. And this gate current non-zero value is nothing but what input impedance is almost zero, but we had a maximum input impedance, the gate voltage was, gate current was zero, right? So when EG, so this is what we mean by the tunneling current. As we keep on decreasing our oxide thickness, there will be gate current. And this gate current is non-acceptable in the MOSFET. Okay, and that's why this is one of the non-ideal characteristics, and this is one of the secondary effects because of the short channel. Okay. Why short? It is nowhere related with the short channel. The moment we are reducing the channel length, in the proportion way we are reducing the oxide thickness also. That's what we mean by. Okay. And the last thing, as you have seen in your all your diodes and the BJT, the temperature is again one of the parameters that affects the working of the MOS transistor, especially the short channel transistor. As the temperature increases, you know the mobility of the electrons, what really happens. If any changes in the temperature affects the mobility of the electrons of the carrier, then obviously there will be a change in current. Okay? So these are all the non-ideal characteristics or a secondary order effects, secondary effects of a short channel transistor. The subthreshold current, meaning even though VGS is less than VT, okay, ID, which is a ID is no more zero, it is non-zero component, and that's what we mean by this. Body effect, if it doesn't take care of the fourth terminal, the VT starts increasing, and here VT start decreasing. You can see the aspects of here. Subthreshold conduction, the VT starts increasing. We assume, I mean, this is what the conclusion we came. The moment I starts increasing my VDS beyond some value, near the source, the barrier lowers and there will be a current. That means before VGS enhances the gate channel, there will be a current. That means we can say that virtually my threshold voltage is decreasing in the subthreshold conduction, and in the body effect VT is increasing. In the channel length modulation, you can see that IDS is proportional to VDS. It will never be a constant. It will never be a constant. It will be increasing with respect to increase. It is not linear again, but it is proportional. As VDS increases, IDS also increases. Velocity saturation, they say that because of the channel restriction, no more carrier generation, the saturation, the velocity with which the carriers are moving will come to an saturation. Mobility degradation is with respect to the vertical field and the scattering of the carriers inside the channel. That reduces the mobility. Tunneling, because of the oxide thickness reduction, there will be a IG, that is the current flowing into the channel, and that IG becomes a non-zero component. Junction leakage, again with respect to the fourth terminal, the moment we have to take care of the fourth terminal, whether to be connected to maximum or the minimum potential, ensuring that the PN junctions are in the reverse bias. And the last one, we have to again take care of the temperature, okay, because temperature also plays a significant role in the operation of the conduction of the MOS transistor. Okay, so this is all about for the today's session. Okay, so any clarification, doubts, I'm happy to take up. Yes, any clarification, doubts? Yes, Mahendra.